So now we want to look at how does the calculus work when we have a vector valued function as opposed to a regular function. And it's actually pretty straightforward. The calculus gets more complicated when we look at multivariable functions, but with vector valued functions, it really doesn't change too much from the single variable functions. And that's just because of how these vector valued functions are made up. So if you remember our definition here, okay, so r of t is equal to f of t times I hat plus g of t times j hat. Okay, so f of t and g of t are not vectors themselves, right? These are actually just scalars. It's the I hat and the j hat that are the vector parts of it, right? So when we go to do calculus with these, it's really just going to be, boiling down to how we did the calculus before with the single variable functions, because these are single variable functions. The components themselves are single variable functions. Okay. So there's, just like with regular limits, there's kind of two definitions of the limit here, one more rigorous and one more practical. So back in like Math Tools 1, for those of you who took that class, we looked a little bit at the precise definition of the limit. So there is like an equivalent one here where instead of like the absolute value, you're replacing it with the what we call the norm, which in this case would be the magnitude. It's the magnitude of the vector. It's a special case of another concept that we call a norm, which is just basically something that induces some kind of distance. Okay, so I'll skip over the precise definition here, but if anybody found that one helpful, know that there is one out there, that you could get into. So the limit here. So if we looked at the limit as, say, t approaches a of r of t, then this would be equal to the limit as t approaches a of f of t. And then we usually will put these in the brackets here, and then I hat will be out here by itself. Plus, same thing with g. Okay. So it basically just works exactly like we would expect based on the fact that you can take the limit of sums individually, right? We've seen that before. So here we're just breaking it up over the sum. The vector parts of it just basically don't get in the way of that. So it's no, in practice, it's really no different than how we would normally take a limit. We're just taking basically two limits now. Or if we have a three-dimensional vector, we would take three limits. Okay. So to do an example here, if we do the limit as t approaches 3 of t squared minus 3t plus 4 I hat plus 4t plus 3 of j hat. Okay. So we're taking the limit of the whole thing, just to be clear. Okay. So we're going to take the limit of just the first part and then the limit of just the second part. And this is a pretty straightforward limit, right? We just do direct substitution. So 3 squared, we get 9 minus 9 plus 4. So we get 4. And then the I hat just kind of comes along for the ride. So notice that in the definitional limit here, the I hat just stays there. And then 4t plus 3, so that's going to be 15 j hat. Okay, so nothing more to it. So we just get 4i plus 15j. So when taking the individual limits, all of the same kind of rules will apply. For example, the definition of continuity will be the same. Basically, it'll be continuous if the limit is equal to the output of R. When you're evaluating these limits here, you can use algebra to simplify them and get the limits. You can use L'Hopital's rule if you need to. Because these are single variable functions, you're just taking the limit of a single variable function on each step. So everything regarding limits will still hold true. So with limits being able to just be broken up over the components like this, it shouldn't be too surprising to see the same hold true with derivatives, because derivatives are just limits, right? So it's kind of the same idea here. So if R of t is equal, I'm just going to use component form here just to save us a little bit of time here, not writing out the whole big thing every time. So f of t and g of t are the components of the vector. Then r prime of t is equal to f prime of t and g prime of t. Okay. So same exact thing. You just take the derivative of each of the individual components. Okay. And then a lot of the derivative rules will apply. Like, for example, the normal product rule will apply to the dot product and the cross product. The chain rule will still hold true, all that kind of stuff. So basically everything will stay the same because we're just, again, boiling this down to just taking the derivative of single variable functions. So if we look at this one, for example, right here, t squared minus 3t plus 4, t squared minus 3t plus 4, and 4t plus 3. Okay. So if this is r of t here, then r prime of t is going to be equal to 2t minus 3, comma 4. Okay. So of course we're differentiating here with respect to t as the variable. So if you wanted to write this as dt of r of t, that would be fine too. Whoops, I forgot my vector here. Okay. So the meaning of the derivative will be a bit different here because we're looking at how does x change and how does y change as t changes, right? Since we're differentiating with respect to t. So for example, if we had r prime of, say 1, this would be equal to negative 1, 4. So this is basically telling us that the change in the x value, the instantaneous change of the x value when t is equal to 1 with respect to time is negative 1. It's going down 1. And the y value is going up by 4. Okay. So similar idea to slope, but it can be a little bit trickier to visualize because, on the graph with these kind of vector valued functions, the time variable is kind of invisible in a way, right? It's not an axis. So it can be a little bit hard to spot. But that's kind of what makes the math so useful, is because then we don't have to rely on the graph. We can just calculate it mathematically. Okay. So then integration, the last part here, the last big calculus topic here, right? Again, works the same exact way. So the integral of r of t with respect to time is equal to then the integral of f of t with respect to time, I hat, plus the integral of g of t with respect to time, times j hat. Okay, so the integration works exactly the same as well. So if we were to integrate that same one, what was it, t squared minus 3t, I don't know if that was right. Oh yeah, it was right. 3t plus 4, and then 4t plus 3. Okay, with respect to time. So we're going to get this one will get t cubed over 3 minus 3t squared over 2 plus 4t plus a constant. And then we'll have 2t squared, right? Yeah, plus 3t plus another constant. So we might want to differentiate these constants, call it C1 and C2, just because they don't need to be the same number, right? Now, if we're writing it out in the unit vector form, then sometimes we might write it like, we might combine the constants. So plus 4t I hat, and then we might have 2t squared plus 3t j hat, and then we might have a constant vector. Okay, so we basically, the idea here is that this is equal to, you could have plus c1 I hat plus c2 j hat, and then these you can combine into a single vector, which we call C. Okay. So it's basically just a notational thing, right? In practice, you would, maybe be able to figure out what that constant is or something anyway. So then it wouldn't be a big deal. And then if we're doing the definite integral, again, same rules apply. You would just have the bounds and you would plug in your values here. And then there would be nothing different from, this form of integration here. So just to show a quick example of that, like if we have something like 0 to 1 of, 2t comma 3, then this is going to be, and sometimes we might actually just write it like this. Okay, comma, we might just write it inside the component vectors here. Okay, so this is going to be t squared from 0 to 1, comma 3t from 0 to 1. So that's going to be 1 minus 0, so 1, and this one's going to be 3 minus 0, so 3. Okay, and then we just end up with 2 numbers since we plug in the bounds here.